Hi, I'm Rex Black, President of RBCS. Welcome to the RBCS YouTube channel. Hey, I hope you enjoy all these free resources that are available here. And do us one favor. We need to keep the lights on and we need your help to do that. So, when you need testing and quality related services, training, consulting, expert services, you name it, let us be one of the bidders on that next job. We don't expect to get all of your business, but we'd like to get a chance. Thanks and enjoy the shows.
On behalf of RBCS, welcome everyone. Today on this webinar on the ongoing suckiness of software quality and why it happens. I am Rex Black, President of RBCS, a worldwide testing and quality assurance firm serving clients ranging from small startups to Fortune 20 global enterprises. Since 1994, we have delivered insight and confidence to hundreds of clients around the world. We have a team of international consultants who deliver customized training, consulting, and outsourcing services for companies that are looking to improve their test and quality assurance practices. I'm the author of many books on software testing, as well as being the past president of the ISTQB. Attendance at today's webinar does earn PMI PDUs. I would like to thank Vicki Sasser for reviewing the materials for PDU status and for making valuable suggestions. Attendees will receive an email telling them how to claim PDUs, including the PDU code. PDUs are available for live webinar attendance only. Before we start the presentation, a couple notes. If you have any questions, feel free to submit them at any time during the presentation via your webinar interface. Please note I will be answering them at the end. There is no need to ask for presentation copies. The presentation is on the web, rbcs-us.com, in the basic library. While you're there, check out our new mobile-friendly website, which just kicked off on Friday. And so far, so good. We haven't had anybody tell us that they've had problems with it, and we've had people say they like the way it looks. So take a look at it. By attending this webinar, you are automatically registered for the free e-learning drawing. So check your email over the next couple days and watch the spam filter. I hope you enjoy this free webinar from RBCS. We do these free webinars as a service to the software testing community because at RBCS we are a not just for profit company. So you may not know who this guy is, this guy that you're looking at here on your screen, but if you don't know, he's the fellow is named Sisyphus. Sisyphus got the gods, the ancient Greek gods, angry at him and was condemned to spend every day carrying or rolling, depending on the version that you read, a stone up to the top of the hill, and once it got to the top of the hill, the stone would then roll down the hill, rolling over him in the process. As you can see, he's being not exactly assisted, but hindered by various nasty, nightmarish-looking critters there. I think this might be a Hieronymus Bosch painting, but a similar style anyway. So you can maybe relate to Sisyphus now. You feel like, God, I spent my whole career working on improving software quality, and it still sucks. Why? Why is software so bad? So, a good question. Now, it didn't start with the beginning of your career or the beginning of my career. Not sure which one came first. Mine was in the early 80s. Software quality has actually always been bad. And in fact, software quality was bad before there was even software, or at least there was thought of it being bad, as I'll explain later. The difference is that now, unlike in the 50s, software is actually absolutely everywhere. You are almost certainly within arm's reach of software at this very moment, possibly two repositories of it, the PC and the smartphone. And those two items and the software on them are just crawling with bugs. And these bugs are very, very expensive. They cause a tremendous amount of damage to the world economy in terms of lost productivity at the very least. Excuse me, sometimes other damages. And in some cases, people get killed due to software bugs. That's not so great. These bugs are not just a matter of irritation. They are drain on the economy and a threat to human safety. So given that that's the case, how is it that we're putting up with this situation? Why is this acceptable to society and to governments and to individual purchasers and enterprises? What's the story? Why do we collectively put up with software that sucks? I mean, after all, if you look at our colleagues in the world of manufacturing, they are able to achieve Six Sigma levels of quality. And if you're not aware of what that is, I will be explaining that here today, comparing software quality to manufactured quality. And I mean, geez, we're high tech. We should be better, right? I mean, if you can consistently turn out a can of beans that doesn't give people botulism, then shouldn't we be able to consistently turn out software that doesn't waste people's time or potentially kill them? So what's in our way here? So Six Sigma. Let's talk about Six Sigma levels of quality. What is Six Sigma? A Six Sigma level of quality. Okay, so this is statistical process control stuff, and if you're familiar with the whole Six Sigma black belt kind of thing that was a very big deal in the early 2000s, popularized by its use by Motorola. Basically, Six Sigma refers to you have a process, and this can be like manufacturing beans, canned beans, for example, and the process has a specification size or something to it. Let's say that when the lid is put on the can, that the machine that's putting the lid on the can has a certain diameter that it's aiming for. Okay, say, I don't know, 10 centimeters. Well, not 10 centimeters. 10 centimeters, let's say, or 20 centimeters or 8 inches, what have you, right? So that's the specification. Now, the thing that happens in manufacturing is you always get some variation around the target. And at some point, what would happen if the lid of the can is not a right enough size, close enough to that target of 8 inches or 20 centimeters or what have you, that the can won't actually properly seal, and you're going to have a spoiled can at that point. It won't properly seal; it'll leak, and that potentially has safety issues. So the variation is going to tend to follow a normal distribution, which you're seeing here with this figure that I borrowed from apotokyo.org. So you see that. Let me get a highlighter up here so I can kind of. So let's say this is our specification of 8 inches. Okay. Now you're going to get some sort of distribution around that target, and there's the upper specification limit and lower specification limit. These are the acceptable ranges of variation. Say 8.05 inches here, and 7.95 inches here. And so if it's less than 5, if it's within 5/100ths of an inch of 8 inches, it's going to be acceptable. And if it's outside of that range, it's going to be unacceptable. It's going to be waste. So basically, outside of these red lines, any can that comes off the line that's outside of these red lines is going to have to be thrown away. Now, the number of items that fall outside will be statistically determined based on the distribution here. And so what we're seeing is one standard deviation, or one sigma. At that point, only 31% of the area of the curve is actually inside of these two red lines. So in other words, 69% of the cans coming off the assembly line would be waste. That's 1 sigma level of quality. That's obviously unacceptable. Now, if you can get it up to 3 sigma level of quality, 93% of the stuff coming off the line is going to be acceptable. You're going to be wasting 7%. But if you get to 6 sigma level of quality, that's what's shown here, there are basically going to be 3 defects per million items coming off of the line. Okay, so that's what you're targeting with a 6 sigma level of quality. You want to have your machines all calibrated such that they are producing something where the item is on average exactly as specified. So in other words, if you average together across 1 million cans, the average size of the can is 8 inches exactly. It's not slightly above or slightly below, and that you've got 99.9997% of the cans are within that 0.05 of an inch tolerance. Okay. So, software. What about software? How are we doing with software? Well, not good. Okay, we comparatively suck. So Capers-Jones has done a bunch of studies, and what he shows is that typically software industry typically releases 13,000 defects per million lines of C++ code, which would be about the same for Java. Okay, that's following a typical development practice. And that's after 85% of the defects have been detected and removed. So defect detection effectiveness would be 85% or above. In other words, if we find 85 defects during testing and the customer subsequently find 15 defects, we have detected 85% of the defects. So that's 85% defect detection effectiveness. Doesn't necessarily mean that those defects will all be removed, but one would hope that they would, or at least some significant number of them. Now, we have clients that regularly achieve 99% defect detection effectiveness. So they find 99 bugs in testing, 1 bug goes out to customers undetected. So, I'm not saying that that's the exact number, but of 100 bugs delivered to the test team, they will find 99 of them and miss 1. Now, so let's suppose that we could push everybody up to that 99% defect detection effectiveness, and let's suppose that every bug that we found got fixed. Well, you would still be releasing close to 1,000 defects in a typical million-line C++ program. Oh, okay, well, geez, that's not, that's a long way from 3, right? Because 6 Sigma would say that we would have 3 defects per million lines. But actually now, that depends on how we measure our 6 Sigmas, doesn't it? So we're saying, okay, each line of code is an opportunity to have a defect or to have to introduce a defect. And deliver a defect to a customer. That's one way of looking at it. But we could also say, well, what about the fact that unless you have some sort of defective copy system in producing copies of the software, actually every bug that is in one copy of the code will be in all copies of the code. So in fact, your yield is 0%. In other words, 100% of the copies of the application have those 1,000 or 13,000, 1,000 being best case, 13,000 being typical case, defects. So, that's really bad. So this is why I'm saying software quality sucks, because compared to manufacturing, We do, very badly. All right, so I made a point at the outset that bugs have been with us since the start. So this is the famous Grace Hopper bug report that actually has a real bug on it, and is historically the source of the name bug to describe a software defect. Though actually Boris Beiser has an interesting essay that he wrote where he it defends the use of the word bug for a software defect and says that it might very well predate that. And this would just be a coincidence. Obviously, they had been talking about bugs in the software because notice that Grace Hopper says first actual case of bug being found. The bug the bug had actually shorted out a relay, as you can see here. Now in fact, the possibility of bugs in software, whether we're talking about physical bugs or bugs as a concept of something defective in the software, goes back even further than that. So apparently Ada Lovelace, who for whom the computer programming language Ada was named, and poor Ada, I mean, she has a computer language named after her, which is nice, but it's probably one of the least successful languages of modern times. Anyway, Ada Lovelace was the person who was going to program, or hope to program, Babbage's proposed and never actually realized analytical engine, which was, if I remember correctly, based on the automatic looms that had been developed, and he'd come to the realization, hey, we could use those to do calculations. But one of the things that she pointed out was, well, yeah, but you could have bugs in those. You could have errors in the program itself, and then you'd get the wrong answer. So bugs have been with us since the start, and if we take the numbers that I was talking about on the previous slide, and then make the very modest assumption that there are about 10 million apps in use, which I say is modest because there's probably a good 7 or 8 million apps on the various mobile device app stores. Certainly more than 10 million, but if we assume 10 million apps in use, that would mean that there are trillions of bugs in the wild out there in the software. And again, as I said, every piece of software out there is almost certain to have bugs. There's I've yet to see anything other than trivial software written by first-year college students that could possibly be called bug-free. And of course, it's also user-free, which makes it easy to be free of any user-reported bug. So this is again dismal. It is simply just a dismal state of affairs, because remember, every one of those things is defective. We have effectively 0% yield compared to 99.9997% yield for modern manufacturing. All right, so excuse me. The core of our problem here is that software engineering is not a true form of engineering yet. It can be, and hopefully ultimately will be, but at this point it's not. And the best way to convince yourself of that, if you don't want to take my word for it, which you shouldn't, you should be listening to me with full skepticism in deployment here, because I'm saying some I don't know, maybe not outrageous things, but certainly I am confronting you and everybody else in this profession, assuming that you're a software engineer, and I'm confronting myself too with an assertion that what we do is of very bad quality. And so I would hope that you are listening to that and saying, okay, I want to ask some questions here about this. So here's my point. Why do I say software engineering is not matured to a true form of engineering? Well, think of how a bridge or an aircraft is designed or built. So you have, ironically enough, computer-aided design and computer-aided manufacturing systems that are used to design bridges and design airplanes and to subsequently uh, create the materials that those things are built from. And we can predict in advance the load capacity of a bridge. We can predict how it's going to respond to high winds and earthquakes and those sort of things. And it would never be the case that knocking a single rivet out of a bridge would cause the whole thing to collapse. But such things happen with software all the time that you know, oh my God, how'd that happen? I only changed one line of code, you know. I mean, it's, and can you actually model the functional behavior of the bridge and predict how it's going to behave under certain circumstances? It's pretty limited in terms of what we can do there. Reliability and performance, yeah, to some extent, but you know, you talk about security and functionality and so forth. No, that's you know, it's not subject to that. There's been efforts to try to do things like proofs of correctness and so forth for software, and it's all fallen flat on its face. So you know, we are way behind our fellow engineers in the civil engineering and aeronautical engineering world. And there's this great quote from Frank Lloyd Wright that I came across serendipitously right as I was creating these slides. It said, you can use an eraser on the drawing board or a sledgehammer on the construction site. In other words, to correct a defect. It's easy enough while you're drawing out the the way that the bridge is going to be built to go, oh, wait, that's wrong, and fix it. But once you start building, you know, yeah, it's going to have a lot of cost. Now, people will say, oh, no, that's not true for software at all. I mean, it's really easy. We just fix the bug and, you know, shoot a new version out there and, you know, everybody updates. Or if it's software as a service, then, you know, it's just people are automatically going to get the fix. Well, yeah, but that you can't unring a bell. If you have put software out there that has wasted a bunch of people's time, that lost productivity is not unlost just because the bug was quickly fixed. Any more than if a span of a bridge collapses and a bunch of cars fall through it, and you say, well, we can fix that span of the bridge real quickly. Yeah, but the people who are in those cars are dead. The cars are destroyed, you know. And you might say, well, you know, that's you know, you're being hysterical here about this because, you know, does software really kill people? Well, yes, it does. There was an incident in Houston where a doctor, ironically enough, in a hospital, got trying to catch an elevator, got caught between the door of the elevator, and while this is not supposed to happen because the software is not supposed to allow this to happen, the software allowed the floor to move while the door wasn't closed. And it acted as a slow motion guillotine on this guy. It was not a survivable injury. And I could go on. I mean, there are others. So those circumstances, those consequences cannot be undone, no matter how plastic and easily fixed software is, and software bugs are. It's you know, you can't undo the damage. Now, okay, so, you know, this is my rant so far, is that we're in the place that we are in with respect to quality. It's bad, and the reason that we're there is because we have not evolved software engineering into a true form of engineering yet. And, you know, it does make sense that would take a while. I mean, it did take quite a while before before aeronautical engineering, which, you know, came about probably in the I guess you could say 1905, 1910 time period. You know, it's taken you know, 100 years to get where we are with that, and probably took about 50 years before it was really, you know, true engineering. There were some pretty spectacular mistakes made with the early jet aircraft, for example. So, you know, we're going to have a ways to go. We are where we are, but what do we do that makes things worse while we're waiting for the for software to evolve to a true form of engineering? What mistakes are we making that make the consequences of this worse? Well, there are some. And you know, let's look at them. Probably just the way to best summarize this is that, you know, if you look at Jones's figures, like I said, 13,000 defects per million lines of C++ code is typical, but by ratcheting up your defect detection effectiveness to 99%, you can get that down to 1,000 defects. So that's an order of magnitude fewer bugs. And assuming that we are smart and we focus our testing on the most important bugs, one would assume that that would actually be more than an order of magnitude in improvement in terms of the user's experience of quality. So why is this? Why are we inflicting 10 times as many bugs on people as we could? Well, I mean, a lot of it is just because if you go and you look at the way people develop software, you know, it's 25 plus years in the past. Best practices are not in deployment, as it were, and software testing is even worse than that. I mean, there are techniques like equivalence partitioning and boundary value analysis that have been described in easily accessible books, Art of Software Testing, for example, for 40 plus years. But I still find testers who don't know them, or they know them, but they don't use them. They don't know how to use them. So, you know, if we apply these techniques, that's how you get to that defect detection effectiveness of 99%, and that's how those defects get removed and fewer defects get put there in the first place. So what's standing in our way here? Well, probably one of the biggest problems, biggest root causes of sloppiness, which is, I think, a fair way of saying fair to follow best practices, is schedule pressure. So you get these unrealistic schedules that get put in place. They're driven by marketing pressures, and you know, there's ideas that well, you know, we absolutely got to be first to market, et cetera, et cetera. And you might say, well, we're agile, so we don't have schedules. Oh, you certainly do. You have a schedule that every 2 weeks or every 3 weeks or every 4 weeks, you're going to have to produce potentially shippable software. And the way that this problem manifests itself there is not too short of a schedule. It's too much in each iteration. And I've seen this happen plenty of times. And yeah, you're supposed to be able to use burn down charts to try to measure how you're doing and so forth. But, you know, I mean, you still see it. I mean, people want what they want. And when that collides with reality, they still want what they want. And this problem has existed since the beginning of software engineering. You've got Fred Brooks in the Mythical Man Month describing IBM projects that he worked on in the 1960s. And he's talking about 20 pounds in a 10-pound bucket, and basically this problem of trying to do too much, too little time, and too little resource. And this is a top-down problem. I mean, this is management coming to the individual contributors and saying, you know, thou shalt do this. And then people like go, oh, well, gee, you know, and oh, come on, you be a team player, you know, this is really important. And then when the individual contributors, you know, don't achieve what was never possible to achieve in the first place, then management effectively punishes that failure. Withholding of bonuses, you know, actual, you know, dinging people on performance evaluations, various other forms of punishment or withheld reward. And as testers or in any other quality activity, you know, reviews and so forth that are subject to this as well, you know, what we do is something that is infinitely compressible, right? I mean, I can run one test case and be done testing, quote unquote, in 2 hours, or I can run 1,000 test cases and be, quote unquote, done testing in 5 days or 10 days, depending on how many testers I've got, right? Either way, I'm done testing because I've done all the testing I'm going to do. So this is the thing that tends to happen, and I see this happen. I've seen this happen over the years on lots of waterfall type projects, but it also happens on Agile now where, hey, the sprint's over, so we must be done testing. Really? And that can be exacerbated by the fact that we're not able to calculate defect detection effectiveness, and so I'll come back to that later. So, this combination of schedule pressures and the compressibility of software testing and other quality activities is, going to hurt us. And not only does testing get pressured on the schedule side, it also gets pressured on the monetary side. So you get this lack of funding, and excuse me. I don't hold us, the quality professionals, entirely blameless in this, because I don't know that we always do a good job of making the business case. And there's a very compelling business case to be made using a very well-established quality management technique called cost of quality. But a lot of people don't know how to use cost of quality to make the business case for testing and quality. And if they do know it, they don't necessarily use it. And, you have to understand that our predicament here is different than the predicament that the developers are in. I mean, yes, the developers are going to be pressured and put under schedule pressure, but, everybody understands that without developers, or with fewer developers, you get less code, and without developers, you get no code. But, one tester, 10 testers, I mean, I still get testing, and I still get to say I've done some testing. And this is where we kind of get ourselves in a trap, and why we really need to be able to quantify things like how much risk mitigation are we providing and how much savings are we providing in terms of cost of quality and so forth. Because what you see is that the average software development professional, software engineering professional these days, and even sales and marketing people, are what I call vaguely religious about testing and quality. Now, what do I mean by vaguely religious? Well, it's kind of like if you look at sociological studies that have been done in the United States over the last 10, 20 years, most people in the United States will say that they have a religion. There are actually very few self-described atheists in the United States. Now, this is just a sociological metaphor here. I'm not making an argument one way or the other. So 95+% of people in the United States will say, oh, yes, I've got a religious faith, and they'll be willing to say, okay, this is what I believe, and this is my religion. But what happens if you drill down on that is really interesting, because if you ask people, well, when was the last time you were actually in a mosque or a synagogue or a church or a temple, it gets, this is my brother-in-law's bat mitzvah, or my sister's wedding or something like that. So not very frequently. So again, the metaphor that I'm making here is that people in software engineering feel about testing and quality the same way that a lot of people in the United States feel about religion. They say they have it, but they don't set aside a lot of time and money for it. Okay, so it's our job as quality professionals to do a better job of convincing our fellow software professionals that they need to set aside more time and money for testing and quality. Not because it's better for us as the quality professionals. That's a total loser argument. I want you to give me more money because I will be happier, is the worst possible argument that a test manager can make to anybody with budgetary authority. You will never, ever get more money with that argument. You got to basically, the two important things to remember here about making a business case for any kind of change, including increasing the amount of funding for testing. One is that people move away from pain about 10 times faster than they move towards a desired state. This is why, People, make New Year's resolutions and they sign up for the gym and all that stuff. And, the gym is packed in January and half of those people aren't there by about this time in the year because the desired activity is to be healthy, right? But you want to find people who are really serious about exercise and working out. Show me somebody who's, under active doctor's care for diabetes or has had a heart attack or something like that. Those are the folks who are going to join the gym and stay in the gym because that's necessary to move away from pain. Now, the second thing here is when you're going to talk about pain and alleviating pain and using that to motivate change, don't talk about your pain. Nobody cares about your pain. Your mother cares about your pain. Your father cares about your pain. Your relatives and so forth care about your pain. But, at business, your pain, that's not an argument. You got to make it about the organization's pain. Be able to point to this is how much money we are losing every year because we ship buggy software. Cost of quality will allow you to do that. Point to problems that happen in terms of things like performance and reliability, and this is why we need a more realistic test environment so that we can do more realistic performance and reliability testing so that we don't have the kind of disaster that we had on product X, right, where you're able to point to something that was released 3 months ago and was a disaster. Okay, so learn to use these techniques to proselytize for better quality. And we also need to do a better job of measuring quality and the impact of not having it. So, I was using defect density because we've got it and it's easy to measure, but it's really kind of a fairly weak surrogate metric for quality. You could have two applications that had the exact same defect density, in other words, the number of defects per million lines of code, that would be of a very, very different level of quality just based on customer satisfaction and fitness for use, depending on what kind of defects they had. And so we don't really have good measures here, and where we are able to do measurement of things like, what level of risk are we taking by using risk-based testing and using traceability of our test results back to the risk to be able to say these are the risks that are mitigated, these aren't. Being able to talk about confidence, building, and by talking about code coverage, or not code coverage, but requirements coverage. We don't always do this very well. And it is certainly the case that when we have good measures, we don't always use them as effectively as we could. We sometimes, when we're as test professionals, quality professionals, saying, results aren't so great, blah, 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 look at all these failures. People say, oh, geez, you guys, you testers are always being negative. Come on, it's going to be fine. I remember giving a presentation once on just some abysmal testing results. And then, I was told, look, like that, none of those bugs are customer facing, whatever that meant, like a bug, it turns back on the customer. People basically were encouraging me just, tone down the findings. I went into a meeting with some company executives, a separate one-on-one meeting, and I was told before that by the project managers, hey, don't paint too bleak a picture here. The project's going to get canceled. And I'm, oh, okay, great. So in other words, if I go in there and tell the truth, then and the project gets canceled, it's my fault that everybody lost their job, right? It's not the fault of people who built the bad software to begin with, right? That the project got canceled. It's my fault for telling the truth to the executives. Now, we have a similar problem with productivity metrics on software, and there's a great book by Capers-Jones called Economics of Software Quality, which I'd encourage you to read if you get a chance. And he makes this argument that one of the problems that we have is, our estimation is very bad because we we aren't very good at measuring productivity, and so we measure the wrong things. You know, we have trouble measuring quality, we have trouble talking about quality, we have trouble measuring productivity, and rewarding for good productivity and good product quality. So, you know, surprise, surprise, people make bad staffing choices. You know, insufficient staffing in certain areas. So we really do need to get better at this, and, you know, there are best practices out there. But you know, we need to adopt those and adopt them in a uniform way. So, you know, people are looking at cost of quality. People are looking at defects. They're categorizing defects using the same scale, so we can start to benchmark our organizations against industries. And it'd be great if we could develop some sort of industry wide pool of defect data that could be studied. I mean, there's a number of things that we could do. That we're just simply not at this point. Again, you know, I'm talking about stuff that can be done now. The long-term goal is, of course, you know, becoming a true form of engineering, but, you know, we're not there yet. Now, as long as we are not a true form of engineering, what we really are is more like a craft than engineering. And I actually gave a presentation on this a while back, where I talked about this, you know, what attributes of something being a craft rather than being engineering. And, you know, I mean, people like to buy, you know, craft-built furniture and so forth, or craft-built armoires or you know, cabinets for your kitchen and that sort of thing. It looks all very nice, but you would not drive over a craft-built bridge. You know, would you? Oh, proudly built by the craftsmen of San Francisco. Here's a bridge. You're going to drive over, you know, 10 kilometers or 6 miles of water. No, you wouldn't do that. What people who build bridges are licensed professional engineers, at least the people who do the design and so forth. Now, standing around and, you know, pouring asphalt and concrete and riveting I-beams together, those are just, you know, plain old construction workers. But, you know, we're not in that place at all with software. We're not, you know, we have to be a true form of engineering in order to achieve that. So in the meantime, basically, most of the work that's being done with software, ironically enough, is hand done. And I say ironically because, again, remember, the ability to build these enormous bridges and this tremendous airplanes and so forth is all enabled by software. So software allows other engineering professions to do things that the software profession can't do. So if you look at the people who are building bridges and designing airplanes and so forth, these are licensed professional engineers. Okay, what makes somebody a software engineer, a software tester? A lot of times it's just because they said so. And, you know, you could say, well, that's absurd, but the thing is that because the widespread failure to follow best practices is so pervasive, so pernicious, you know, is it a surprise that, you know, anybody can say they're a software tester? Well, if there's no expectation or very little expectation that people who are doing software testing are going to know core best practices, some of which have been around for 40 plus years, you know, what makes qualified? Well, I mean, at some point we just have to start saying, no, look, let's get these quality and productivity measures in place, and let's, you know, start to measure what happens when you have qualified versus unqualified people. Because if you can't do that, one of the things you get is what we got starting in the 90s and what continues now, which is this race to the bottom with outsourcing of software development. No offense to folks who are listening to this who are working in outsourced, you know, offshore software development entities, and I'm sure that some of those do very good work. But the main thing that has driven companies to move development work and testing work to other locales outside of their offices is not convenience, because it's inconvenient to have work distributed. It's just harder to manage. The thing that's driven it is people look at costs. They're like, whoa, okay, you know, $10 an hour for a developer in wherever versus, you know, $150 an hour for a developer in the United States. Oh, okay, that's a no-brainer. You know, we're going to do that. Well, it's a no-brainer if what you are buying is hours of people's time. But of course, you actually don't care about hours of people's time. What you care about is the quality and the volume of the features produced. So, again, back to needing good quality and productivity measures. What can we do about this issue of qualifications? Well, certainly, if we can say, look, we want to see people with good, reputable, credible, valuable certifications in software development, in software testing, and that should just be seen as an entry criteria. Now, I know, you know, people don't like that, and they go, oh, well, you know, should I have to take this test, and why should I, you know, to take this training? I'm not saying training here. I'm saying passing an exam, and you know, be skeptical here again about these exams. You know, talk to the people who are providing the certification about how the exams are developed and how the exams are proven to be credible through psychometric analysis and so forth. You know, and that's the kind of thing that we should be insisting on. This is not about just passing an exam that was put together by, you know, who knows who. And this is about having passing an exam that's actually credible and that tests your abilities against, you know, established learning objectives that are consistent with best practices. Excuse me. So the thing that I would say that is one of the most toxic elements of what's happening here with software quality is that you have software companies that are effectively able to transfer the cost of their bugs onto their users and customers. Now, this kind of varies. So, you know, a lot of times when companies hire third parties to develop software for them or use outsourcing firms, there's what's called a warranty period of 30 days or 60 days or 90 days, and any defect that's found in that period has got to be fixed at the vendor's expense. But, you know, you look at like large enterprise software companies, and I'm not going to name names here because it'll sound like I'm picking on people, but you could figure out who I'm talking about. Companies that sell software to other companies that those companies use to manage their workplace. Most of these enterprise software companies make more money from supporting from technical support, basically selling bug fixes, than they do from selling new software. Why would that be? Why would, you know, this is like if a car dealership made more money from its shop and repairs than it did from selling cars. What kind of incentives would that create in you know, the car business, right? Basically, what happens is a lot of times companies that create software are financially incented to release software that meets minimal quality standards. That's it, right? If they can get it out the door to the customer and it looks like it's kind of sort of good enough to use, then you get them hooked effectively, right? Especially if you're talking about enterprise software or any other kind of software that's got high barriers to exit, where it's really expensive to change. I mean, imagine just, for example, how bad would Microsoft Windows have to get before all the companies using Microsoft Windows decided, you know what, we've absolutely had it. We are going to Linux. Linux is free. The quality of Linux is better. And we are just going to figure out how to do without Windows and without Microsoft Office, so on and so forth. The barriers to exit there are huge. This is why, you read stories of companies that left a Windows world for Apple or Linux, and it's just man bites dog story. That's why they're seen as spectacular. Now you might say, well, you know, where the trend is away from buying software anyway, the trend is for software as a service, and so then that's the bugs get fixed right away and so forth. Well, yeah, I would just say that actually increases the issue here rather than decreases it, because it now takes it completely out of your control. Now, I totally accept that this has been a real marketing coup by the people who push software as a service, because it makes accountability for quality even less. And, yes, I've heard this fail fast, Okay, that's easy to say if you're transferring the cost of the failure onto somebody else, right? But there are costs of external failure, and they are borne by someone. It's just, unfortunately, they're not always borne by the companies that incurred the cost of failure. So, what we need really here is some sort of implied warranty of fitness. I mean, if you bought a car and that car was sold to you as a car that was friendly to the environment and got good mileage and so on and so forth, and then it turned out that somebody had actually engineered some hoaxware, some cheats into the software that was allowing it to defeat environmental testing, there would be consequences to that, wouldn't there? Yes, there are. Ask Volkswagen right now. They're looking at billions of dollars in fines. This is going to cost them a tremendous amount of money. But when was the last time that you saw a software vendor held accountable for shipping software with massive amounts of defects in it and the productivity hits? Now you could say, well, this is different because that's inadvertent. I would say, no, I'm calling BS on that. It's not inadvertent because application of best practices, as I just showed, can reduce the number of defects by an order of magnitude. So this is a choice. There are choices that are being made in this industry that are leading to the current levels of quality or lack of it. So yes, I think an implied warranty of fitness would be entirely appropriate here. And then I think that the software vendors should be held legally responsible for impact to the safety and productivity of the people who buy their software. And if you consider that an outrageous statement, I would just say exchange the word software for any other product you use in your life and see if you feel the same way about it. Now, of course, in order for this to work, we would have to achieve these better quality measures that I was talking about before, because simply doing this based on defect density is not going to be good enough. Okay, so that's my rant, and I'm sticking to it. I understand that I've made people, well, hopefully I've made a lot of you think. I can see from the questions coming in that some of you don't think much of what I've had to say, and that's fine. I did not put this together expecting that this would be received with loving arms by any means. In fact, Vicki Sasser, when she reviewed it for PDU, said, wow, that's really provocative. And I said, yes, that's my intention, was to be provocative. So, to just conclude here, I mean, hopefully you at least agree with me that the software quality problems have been around from the start. Hopefully I've made that case. Hopefully you would also agree with me that we are not yet a true form of engineering. If I haven't made that case well enough, then go and listen to my recorded webinar on towards a true form of software engineering, which will expound on this in great detail. While we are still on that, what's probably a good 50-year path towards really becoming a true form of engineering, let's just stop shooting ourselves in the foot. That's my radical suggestion for the day. Let's stop making avoidable mistakes. I get that we're going to make new mistakes because this industry is, exploding in terms of what we do and the audaciousness of the things we take on. So we are going to make mistakes. And excuse me. But let's not make mistakes that are stupid mistakes, and let's not make mistakes because we're effectively paying each other to make mistakes. Okay, I mean, just a plea to the managers out there listening to this. I mean, please, I hope you understand that when I was talking about management incenting these bad decisions, it's not an attack on you or your integrity, but it is a challenge to you to think about, you know, when you make decisions, when you do people's performance evaluations, when you put rewards and punishments in place, you know, ask yourself really, what kind of incentive am I sending here, especially in terms of quality, you know, and how would I recognize that these are really, you know, going to be toxic incentives. So, you know, why should we do this? Why should we take these things on? Well, because of the importance of what we do. If all we did was make games like, you know, Candy Crush or the Kim Kardashian game or something, no offense to any of you who may be making such things, but if that's all we did was make entertainment software that ran on people's mobile devices, then I guess I'd be a lot less riled up about this. But, you know, I have clients that are in the gaming business, and some of them, and all of my clients anyway, take quality very seriously because people spend a lot of money on those games and they deserve to be entertained by them. And that's the way that they see it. Now, so think, if you're in the business of something beyond just entertaining, but helping people get their work done and possibly saving lives through medical software and so forth, I mean, this stuff really does matter. So, you know, what we are doing is a huge part of the world economy, is impactful on the entire world economy now, basically. So let's just do it better and do the things that we already know how to do.